Transport phenomena in Biosystem Module 4 Shell Momentum Balances Segment 4 Flow through a circular tube. With me, Yusuf from Bioengineering Study Program, School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about the module overview, shell momentum balances, and the flow of a falling film. In this segment, we will discuss about flow through a circular tube. The flow of fluids in circular tubes is encountered frequently in physics, chemistry, biology, and engineering. The laminar flow of fluids in circular tubes may be analyzed by means of the momentum balance as described in the previous segment. The only new feature introduced in this case is the use of cylindrical coordinates, which are the natural coordinates for describing positions in a pipe of circular cross-section. Let's consider a steady-state laminar flow of a fluid of constant density ρ and viscosity μ in a vertical tube of length L and radius r as shown in the figure. The liquid flows downward under the influence of a pressure difference and gravity. The coordinate system is that shown in the figure. We specify that the tube length be very large with respect to the tube radius, so that end effects will be unimportant throughout most of the tube. We postulate that Vz equals to Vz as a function of r, Vr equals to 0, Vθ equals to 0, and P equals to P as a function of z. With this postulate, it may be seen from table B1 that the only non-vanishing components of tau are tau rz equals to tau zr equals to minus mu dvz per dr. We select as our system a cylindrical shell of thickness delta r and length L, and we begin by listing the various contributions to the z momentum balance as shown in equation 422 until equation 426. The quantities phi rz and phi zz account for the momentum transport by all possible mechanisms, convective and molecular. Substituting the terms in equation 422 until equation 426 into the momentum balance of equation 41 results in equation 427. When this equation is divided by 2 pi L delta R and the limit taken as delta R approaches 0, we get equation 428. The first term on the left side is exactly the definition of the derivative of r v r z with respect to r. Therefore, equation 428 becomes equation 429. The components of phi rz and phi zz are shown in equation 430. In accordance with the postulates that Vz equals to Vz as a function of r, Vr equals to 0, Vθ equals to 0, and P equals to P as a function of z, several terms are cancelled. Hence, equation 429 can be simplified to equation 431, which may be integrated to give equation 432. The constant of integration may be evaluated by using the boundary conditions, which results to equation 433. Substituting Newton's law of viscosity into the left side of equation 433 results to equation 434, which is the differential equation for the velocity distribution. It can be integrated to give equation 435. The constant of integration is evaluated by using the no-slip boundary condition at the solid surface, and finally the velocity distribution can be determined from equation 436, and the results are shown in the right figure. Once the velocity distribution is known, a number of quantities can be calculated. First, maximum velocity Vz max, occurs at r equals to 0 and can be determined from equation 437. The average velocity Vz is obtained by dividing the total volumetric flow rate by the cross-sectional area as shown in equation 438. The mass rate of flow W is the product of the cross-sectional area by r squared, the density ρ, and the average velocity as shown in equation 439. This rather famous result is called the Hagen-Poiseuille equation. Last but not least is the z component of the force Fz of the fluid on the wetted surface of the pipe is just the shear stress tau Rz integrated over the wetted area, which can be expressed by equation 440. This result states that the viscous force Fz is counterbalanced by the net pressure force and the gravitational force. For the next segment, we will discuss about flow through and annulus. Until then, I am Yusuf from Institut Teknologi Bandung.